So maybe I'll try to start first to share my screen. Prepare my slide and then okay. So what is outline today for today? So today I propose to first to finish to study the section devoted to the bagging approach, and within this section we will introduce a particular bagging algorithm that is a random forest. Okay, this is a very well-known ML algorithm that is broadly used in economics and finance for many applications, either for regression or classification or whatever. And okay, then we will apply the random forest algorithm and the bagging method on Python with Colab. And for the rest of the session, I will introduce the boosting methods. Maybe I will have time to illustrate the use of a bagging method with Python, but if I don't have the time to finish this part of application, you have all the codes in my notebook Python, okay? I think that the most important is to well understand the global idea and the theory behind the XGBoost model, and then you will understand very easily the function and the various options that are available. So if everybody is here, let me start with a brief reminder about the bagging principles. Okay, the bagging principle is a contraction of two words, bootstrap and aggregation or aggregating, okay? And then the idea is to draw random sample with replacements that are called bootstrap samples, okay? Then to train a model. So in general, it is a decision tree, but I can bag any type of model. And I train a decision tree on each bootstrap sample. And then when I have a new data issued from my test data set, for instance, these individuals, then I will use the decision rule issued from the first tree, the decision rule issued from the second tree, and the decision rule issued from the B CS tree. And then at the end, I have to aggregate, so by a majority voting rule or by a simple average, the decision of all the decision trees that have been trained on the bootstrap sample, okay? And at the end, we have an aggregation. And the fact, the main result is this idea of reduction of the variance. And the main theorem that justifies the use of the bagging is the following. The variance of your bagged model corresponds to when B is large to the variance of your initial model, for instance, the decision tree, times the correlation between the different decision tree trained on the different bootstrap samples. And the more the model are decorrelated, the more the weak models are decorrelated, their decisions are decorrelated, the more you have a reduction in the variance of your bagged model. Okay? Okay, so is there any question about the implementation or the bagging in general or implementation of the bagging? No? Okay, so let me pursue with two notions. that are related to the bagging approach. The first is a out of bag error, and the second the computation of the feature importance. Okay. So first, let me introduce what we call the OOB, so the out of bag error. So we want to compute an error. So an error for regression in general is a mean square error, okay? Or for a classification, it is a probability that your decisions that you take 0, 1, okay, is different from the true 0, 1 observed for individual I, okay? And in general, I learned to you to, okay, when you have a data set, to split it, okay, in train and validation. Oh, sorry, I have a problem. A train and a validation, okay? And okay, a train and a validation, okay? Here you have the test, but the test is only used to compute to make the ex post evaluation of the model. And then, for instance, in the cross validation, remember the old out approach. Okay, well, in the old out approach, you train the model here. Okay. Okay, and then you apply this model on the validation sample to compute a cross validation error, so a kind of out of sample error, okay, a cross validation error. Okay, so if this is an idea to assess what is behavior of my model when I apply this model to new data, okay. And then I will use this cross-validation error to determine the value of the hyperparameters, for instance, but whatever. I can use this cross-validation error just for an assessment. Okay. When you have a bagging approach, you have another possibility to do the same idea, that is to compute an error out of sample. Okay. And this is based on this concept of out of bag error or out of bag procedure. Okay. What is the guess? The trick is the fact that the trees are built on bagged estimator, on bootstrap estimator or bagged estimator, and therefore they do not use all the observation in the training sample. Okay, so let me illustrate this point. Maybe I will start with this example. Let me consider a case in which we have 5 individuals in the training data set. I randomly draw 3 bootstrap sample with replacement, okay? For instance, in the first one, I have individual 2, 5, and 1. In the second bootstrap sample, I have individual 3, 2, 2, because due to the replacement. And in the last sample, I have the third individual 3, 5, and 1. Okay? Then you use this model, this first sample, to build the first decision tree. You use this second sample to build the second decision tree, and you build the third decision tree on the third bootstrap sample. The question is, since here I do not consider all the individuals from my training dataset, maybe it's possible for me to compute an error for the individuals that are not considered here to train the model. I used two individuals to train the model, S3 and S2. Thus, if I want to compute a kind of out of sample or cross-validation error, for this decision tree, I can compute an error for S1, S4, and S5. And so I will compute the error for this individual. And this is the same for the last three. I can compute an error, an out-of-bag error for S2 and S4. Then here, I have 2 plus 3 plus 2, so 7 out-of-bag error. The error, so for instance, as the error is just for instance, in the regression, the comparison between, okay, the forecast of the model minus the true price of the house, okay, squared. If it is a classification, this is the difference between y hat and y, just to see if there is a 1, 1 or 0, 0, or otherwise there is an error. And then we have here all these errors, okay? And then we will use an aggregation so I can compute up for I is equal to 1 to 7. And here I will define, for instance, an MSE, so a mean square error out of bag. And I hope that you have understood that this is exactly the same as if we add a validation and a train, okay? We use this data to train the model and we evaluate the error on the validation sample. This is the same idea, except that here I have only a training data set and there is no split between my training data set and my and the validation. So there is no holdout approach, no scaffold approach, because okay, within this training data set, when I draw bootstrap sample, I do not use all the observations, and thus it is possible to compute an out-of-bag error. Is there any question about the intuition? No question? Great. So the out-of-bag will be defined, for instance, with the MSE mean square error for the out-of-bag forecast or regression. And this is we account of the situation for which the forecast for classification is different from the true value for a classification divided by the number of out-of-forecast errors that I can compute within my sample. There is a theoretical result that shows that, okay, when you have a sample, for instance, of 100 observations, you have approximately 37% of the total training data that is available as an out-of-bag sample. So if I have a sample of 100 observation, I will have approximately 37 points to evaluate my out-of-bag error. Okay, so when I have my test data, okay, so the test I don't consider. So I have my training data set here. I do not make a split between training and validation, contrary to the holdout approach. And here, approximately, I have 37% of the observation of my training data set that I can use to compute an out-of-bag. Okay. So for people who want to understand where this 37% comes from, the idea is very simple. Let us assume that you have n examples in the training data set. Then the probability of not choosing an example in a random draw is n minus 1 divided by n. We have a replacement sampling. So the probability of not choosing n examples from the n random draws is n minus 1 divided by n to the power n. This is approximatively equal to the exponential of minus 1, and this gave you 0.3668. Okay. This is the definition, the idea of this asymptotic result about the out of bag. Okay. So when you have when you have a random forest, when you have a bagging, okay, you have two choices to determine the optimal hyperparameters. You can do a cross validation, so you hold out, etc. As for other algorithm, but for this type of algorithm and exclusively for this type of algorithm, you can use another approach that is the OOB, so the out-of-bag error approach. Okay. So scaffold here, you have the choice. Okay, there is no particular way, criteria to choose between an OOB approach or cross-validation approach. There are two alternatives. This is exactly the same idea. This is to evaluate the error on data that have not been used to train the model. Let me show how to consider, for instance, to the OOB out-of-bag error, for instance, to determine B, an optimal value of B, that is, remember, the number of bootstrap sample. Okay, so on this graph, you have the number of estimator, remember, and this option corresponds to the capital B in my notation, so the number of bootstrap sample. And here you have the OOB error rate. So I think that it is a classification issue, a classification model. So this is a probability as the frequency of error, of the error, so error type 1, error type 2 in a classification. So the cases, we count and simply count the cases in which, for which the model predict 1, whereas the true value is 0, or predict 0, whereas the true value is 1. But this error rate is determined for the out-of-bag observations. So there is a comparison of three models, three random classifier. I will discuss this point later, okay? But let me consider only one of them. For instance, let me consider this random forest. Look, so the out-of-bag error is rate is the following. So what is, according to you, the optimal value of the hyperparameter B for this model? What is your recommendation to me about the value of B? There is no recommendation.
The error must be at its least value, if I'm right.
Yes, yes. In general,
So,
yes, we don't. we try to minimize the out-of-bag error. So B star theoretically could be defined as arguments that minimize the OOB of B. Okay, but in general, I recommend you here to use these values. That is, when you use 50 bootstrapped samples, you reach a minimum value of the out of bag, and when you increase the number of bootstrap samples, the out of bag error does not decrease. Okay, so it's constant. So in order to minimize the costs of implementation of your model, okay, you have to consider, for instance, approximately 50 bootstrap samples, okay? And with 50 bootstrap samples, you reach the minimum value of the out-of-bag error, okay? It is exactly the same. Let us imagine if we have done this type of, we have a validation sample, we have a train sample, we have a random forest or whatever with 20 bootstrap samples, 21, okay, etc. You train your model on the train sample. And for all this model, you apply them here and you compare the error rate, okay? And you determine what is the value of B. So what is the value of B that minimize the mean square error, or the error, whatever the type of the error, the error here. Yes?
So this appears to be the correct value for
Yes.
the max features equal to log 2 and the max features equal to none. But I don't think that it applies to the max features equal to square root. So
Okay. So square root. Yes, it depends on the, okay, because as I said, just I have a problem with my slide. Sorry. Okay. We have three different random forest model here for the same data set, okay? And for this one, it is true that, okay, we have to increase the number of bootstrap sample to approximately 110, okay?
So the optimal value will depend on how the
model.
max number of features was chosen.
Yes, exactly.
As a
Yes,
hyperparameter.
Yes.
Okay.
It depends, in general, the functional form of the models that have been used for the bagging. And maybe you know how random forest works, because for other participants, we'll explain you in a few minutes. This option control for the number of features that are included in the models in the different trees used on the bootstrap sample. And so, but in general, more generally, it give control for the functional form of the model, and the optimal number of bootstrap samples depends on the structure of the model.
Okay, so somehow the hyperparameters are actually affecting each other. So
yes, exactly.
Okay, thank you.
Is there any question about the out-of-bag error? Great. So you can ask to Python to compute the out-of-bag error and make a loop on the given hyperparameters and to check what is the optimal value, for instance. A second point is the fact that, okay, with bagging, we have now the first ML algorithm in my training webinar for which the decision rule is not interpretable. So at the end, we have the average, for instance, of 50 decision trees. Maybe each decision tree is very large, is very depth. And so, okay, even for one decision tree, it is difficult to follow the decision rule, but now we have a kind of aggregation of, for instance, 50 or capital B decision tree. So we have a black box at the end that relates the X, okay, to the prediction. So the prediction Y, which is a 0-1 in a classification problem, or a continuous value for classification. And we have a black box model, and for which it is impossible or complex to understand the relationship between the feature and the decision of the model. And so the machine learning interpretable is a set of methods to try to make to understand the behavior of the model. Okay, and the first tools, which is a very simple tool, there are more sophisticated tools for machine learning interpretable, for interpretable machine learning. Sorry, the first one is a feature importance. So we have a loss of interpretability, and we want to understand which are the features that are the most important to understand why the model predicts a default or not. We have 20 features: the age, the car price, the funding amount, etc. And okay, which are the most important feature to determine if there is a default or not? Not in the true life, but in the decision of the model. Okay. So we want to measure the importance of the variables or the features. And this is really simple because, okay, in a bagging, when you have a tree, you bag the tree, we will compute the impurity gains associated to the variables, and we will average it over all the trees that you consider in your forest or in your bagged. Okay? So let me clarify this point. So definition, the importance of a feature, or feature importance of a or age variable, is the average gain in impurity, so for instance in Gini, associated with this variable, obtained for all the trees trained on the capital B bootstrap samples. Okay, so the formula is not complicated, but there is many sums. Okay, so we don't have to. We have to be very precise. So remember, we have at the beginning a bootstrap sample with an indexed B. Okay, and we have capital B bootstrap samples. I'm interested in a feature G, for instance, the age. Remember that the age, there is also a threshold, for instance, in my first decision node. I say, okay, age is smaller than 12. Okay, whatever. This is why I have a G index, I have a TG for the threshold. Remember the formula. This is the impurity gain when I use the age variable and the threshold TG, and I compute the Gini index on the parent node and the weighted Gini index on the child node. Okay, so here I have the Gini index in the parent node, and here the weighted Gini index in the child node. So, for instance, let us imagine that, okay, we have a Gini index here of, sorry, 0.4 here, and here we have 0.20. So we have delta, which is equal to 0.2. Okay. This measure the influence of the age variable to reduce the impurity from a node to another. Okay. Now, for each bootstrap samples, we calculate the total gain impurity associated to the variable G. Why? Because, okay, in my tree, for the first tree, maybe the age is here, but the age is also used in this node. So it's possible that the age variable is used 2 times or 3 times within a given tree, okay? So we assume for all the threshold, so here we have a threshold of 30 years. Here you have a threshold of 20 years, etc., etc. So we have a sum here for all the threshold value of all the impurity gains that are allowed by the age variable. So this is the sum of the gain in impurity due to the variable xg. And we do the sum here for all the impurity gains for all the variables in the tree. Okay? So for instance, if this value is equal to 10%, okay, what does it mean? It means that in the tree B, okay, remember that I have many trees, but for a given tree, the impurity gain of the age variable in this tree is represent 10% of the total impurity gains generated by all the variables in the tree. It is clear for everyone? Great. So now this is okay. I have the gain. Okay, for age. Okay, I have the gain for relative gain for je sais pas quoi, the car price. Sorry. Okay, and so I normalize the gains associated to age to the sum of all the gains for all features. And this is here that we have the percentage. Okay, sorry. Here, this is not a percentage. Okay. So at this step, okay, I can compute the percentage of the impurity gain due to the age variable in the decision tree B. Okay. And now at the end, you just have to sum or to consider the average of the gains of the variable G, so the age, for all the trees in my bagging, okay? And I compute the average. And this is what we call the feature importance. So the feature importance of the age variable, delta G, is equal to the average of the normalized impurity gains obtained in the capital B trees trained on the B bootstrap sample. Yes, Mirai?
So actually, I have a question. If I understand correctly, the impurity, it was like a parameter that we used to see the percentage of the examples that doesn't it's not part of the group or the child node. So I'm not sure how the importance of a feature can be explained by this, because in my understanding, this means that this variable does not doesn't do a good job in like classifying the examples in the right group. So is the feature importance is how this variable or how this feature has
Okay.
an impact on the model, or and that's it, or if it's a good variable to
Okay.
like explain.
Okay. Maybe I will make a parallel with econometrics. When you have okay, a variable, a model with two explanatory variables. Okay, the idea is the fact that, okay, when you have a variable that is, let us imagine that the two variables x1 and x2 have the same variance. In this case, okay, we just have to compare the value of alpha 1 and alpha 2 to say, okay, if alpha 1 is larger than alpha 2, then x1 will have a larger influence of on y than x2. Okay, at the limit, when we have a variable that has no influence, then here the parameter is 0. Okay, that's why we test for the significance of a parameter. Now let me go back to my okay, to my decision tree. Let us imagine that, okay, I have a child node in which I have a given partition of 0, 1, let us default and not default, and I use a variable that is fully useless. So let us imagine that I use here a rule on x1 to split this parent node, okay? And let us assume that this variable has no influence, okay? So we will put, for instance, if I don't know, if I don't know if the size of my pencil is larger than 5 centimeters, then okay, you are on the left, and otherwise you are on the right. D'accord? So I put a threshold on a rule on x1 and a threshold, for instance, okay, 5. Okay. So here I have the individual that are satisfy this rule, and here no. Okay. If x1 has no impact, there is no link between x1 and y. Okay. Yes, there is no link. Then it is exactly if you do a random sampling within the parent population to determine who will be on the left and who will be on the right. Okay. And so theoretically, you will have the same proportion. Okay. Let us imagine here we have 50-50. Okay. So on the left, you will have 50-50. On the right, you will have 50-50.
Okay.
Because if x1 has no relationship with y, then when you fix a rule on x1 to split the sample, then it will has no impact on the distribution of y on the left child node and right child node. And then the Gini here will be equal to the Gini here. Okay. And so if this variable has no importance, is delta G will be very small.
Okay.
Okay.
It's clear. Yeah. Thank you so much.
Okay. So at the end, I can ask to Python to compute a feature importance. There are many feature importance, so be careful. And in general, you have a message that it is the feature importance using MDI. MDI is mean decrease in impurity. So it is exactly my formula here. This is the mean of the decrease in impurity. So, for instance, in this example, features 0, 1, 2, etc. You have the mean here of the decrease of impurity, and you observe that the feature 0, 1, and 2 are the 3 most important variables in my model. Okay? And the contribution of the other is very limited. It doesn't mean that I have to withdraw these variables, but it just, okay, the most important variable are features 0, 1, and 2. Do you understand why Python here reproduce this black bar? And do you understand what is what represents this bar? Do you have an idea? Yes, Ahmed?
Are these standard errors or a band of depending on the standard errors? Or is it a maximum and minimum?
Yes, it's a kind of it's a confidence interval. Or yes, maybe Mireille or Fatme.
I was thinking about maybe it's because we have a lot of like samples, bootstrap samples. So maybe it's the maximum and the minimum of
exactly.
all the trees.
Exactly, it is exactly. Okay, let me go back to this formula. Remember that I compute the impurity gains for the variable age or car price, and I have capital B gains, okay? So here I reproduce, Python reproduce the mean of the capital B impurity gains, and here you have the minimum, and here you have the maximum value, okay? So the impurity gains of the first feature range from 0.12 to 0.29, and the average is 0.2021, okay? This is the minimum and the maximum of the impurity gain obtained over the B bootstrap samples, or the B trees trained on the bootstrap sample. Great. Is there any question? This is another presentation of a feature importance with scikit-learn. And so I have this variable, and it indicates that the 2 first variables are the most important in my application. No question? In this case, you don't have the minimum and maximum, but just the average. Okay, let me summarize the key concepts that we have learned together. So the bagging, which is a contraction of bootstrap and aggregation. What is a bootstrap sample? What is the idea of the aggregation of weak learners? The principle of the variance reduction, the majority vote rule to determine the decision at the end, the out-of-bag error, and the feature importance, and the fact that, okay, when you have a bag or random forest, you have no interpretability of the model, and so you have to implement some interpretable machine learning method. Okay, and the easiest method is to compute the feature importance. Any question? So if there is no question, I propose to pursue a few minutes and then to take a break. So I will pursue with random forests. So this is a particular method of the bagging. So the idea is to understand the random forest as a form of the bagging. Just I will apply directly the random forest and not the bagging. It is possible to use to implement here a bagging classifier, okay? But I prefer to avoid to do 2 times the same thing, because, okay, the random forest is a type of bagging. We will apply the random forest because it works in general well, it works well. And so in general, we use a random forest and not the bagging in general. Okay, so we understand the notion of a random forest as a form of bagging. And the main difference is that we have a sampling of predictors. And we will understand the benefits of the random forest and the limit of the random forest and how to implement a random forest. So Breiman, for the third time, so Leo Breiman, a random forest, it is a paper in a machine learning academic journal. Okay, so it is a bagging. And in the context of the decision tree, based on the CART algorithm and based on the previous paper of Breiman, it's very poetical because you have a tree, and then when you put several trees, you have a forest, and the forest is random because you have train your tree on bootstrap sample. Okay, this is the analogy. Okay, we know that the bagging performance in terms of decrease of the variance reduction is a decreasing of the correlation between the individual trees. So if you have an idea to decrease the correlation between the trees, then you can implement it, and then bagging will work better. And this is exactly the idea of the paper of Breiman. The aim of the random forest is to further reduce the correlation during the sampling process. And the trick, this is very nice idea, is to make a random sampling, not only on the examples, not only on the individuals, but also on the predictors or the candidate predictors for a binary. So let me just illustrate with this graph, but with this graph, it is I think it is unclear. The random forest, is the fact that you have the same idea as the bagging. You have a training data set, and you draw bootstrap samples. But so I will take some individuals, in my initial samples randomly. But there is a message here to say, without a color. So it is without a color, it is the idea without some variables. So just to, I prefer maybe to explain you with an Excel file. So I will, if you surprise me, I will. Let me illustrate with the data set. You have. This is a data set. Let us imagine that this is my training data set. It's my Excel file. So here I have the variables, and here I have the credits. What is the bagging? The bagging is based on bootstrap samples. So at the beginning, I will randomly select some individuals. For instance, I will select the individuals 3, 4, 7, 8, 9, etc. in the first sample. In the second sample, I will bootstrap sample, I will draw other, or maybe the same, but other individuals. In the same time, we will make a random draw all over on the variables. So maybe, for instance, I will, among all the 20 variables in my data set, I will select only For instance, 7 of them. Default is a target variable, so it's not a good point. But among the explanatory variables, okay, so let me withdraw this column because this is so here you have the explanatory variable, and among these variables, I will select job tenure, age, loan duration, down payment, credit event, and that's it. Okay. Then I will consider this sample. So I withdraw the rest. Up, up, up. I withdraw other columns and other lines. Okay. And I consider this sample as my first bootstrap sample. So there is a random draw in the individual dimension, and there is also a random draw among the variables. What does it mean? Be careful because, okay, this is, and then I have a data set, and then I will use the CART algorithm, and the CART algorithm will select some variable to build the trees. Okay, but this bootstrap sample will define the training data set for the CART algorithm of the first tree of the first bootstrap sample. It's clear? So maybe the tree will select this variable and this variable, but not the job tenure and not the credit event. Okay, but this is not my problem at this stage. The first is to build the bootstrap sample, and the bootstrap sample is based on the double random sampling, first in the individual dimension, second in the variable dimension. Do you have an idea of why we make a selection or a random sample on the X dimension for the variable? Do you have an idea?
I'm not sure, but maybe we want the model to just have like the variables that is less, to have the model to be less complex, to see if the additional variables are not to be used.
Is not exactly the idea. The idea is rather based on the correlation. Okay, let me illustrate. Okay, with just a few minutes. Let me illustrate. Okay, let us imagine. I will try to find a. Okay, I will right here. Let us imagine that at the first I takes x1, x3, and x17. Okay, for the first sample here. Okay, and for the second, I use x1, x4, and x6. Okay, so this is for the second data set. If I impose here to choose the variables among this set, and here I impose to the CART algorithm to choose the variable among this set, then by consequence, the tree that is the second tree will be largely different from the first one. It's clear? For instance, here you have the age, the car price, and the funding amount. And here you have the married status, the ownership, and the duration of the loan. By necessity, by consequence, it is obvious that at the end, the first model here, the first variable here, maybe it will be the loan duration, here the married status, And here you will have the car price, and here you will have the age. Okay. So by design, the correlation between the decision of the first tree and the second tree will be small. Okay. So the fact that you impose to the model to choose different variables makes the fact that you are sure that the decision of the trees are different from the same individual. Because, okay, here, this tree will use my age, the price of my car, okay, and to take a decision. And it will forecast for me, for instance, that there is a default because I'm young and I buy a very expensive car. This tree is based on my marriage status. I'm married, and my ownership status, etc. And given this observation, forecast 0. Okay. So as you can see, the correlation is low. Okay. And this is an idea to reduce the correlation because it imposes that the structure of the trees are very different. It's clear for everybody? Do you have any question? No? Okay, so let me summarize and then we'll take a break. For B is equal to 1 to capital B. Capital B denotes the number of trees in the forest. You create a bootstrap sample. Okay. Issued for the training set detrain. You train a decision tree with sampling of predictors. So, okay, when you draw the individual. For instance, you take Ramaj, Christophe, and Mireille, but you take also a subset of the exploratory variable from the initial data set, and you train a model. Then you make a second trial, or a second random trial, and you consider, for instance, Nemiz, Fatme, and Ahmed, and then you take another variables and you train another tree on this new data set, etc., etc. Then, okay, you have an option to control the optimal predictor, the set. You will use a set of Q predictor. Remember, we use M individuals in the Bootstrap dataset. Remember, here I have, for instance, 50 individuals, and here I have 2,000. Okay. And you will use Q features or predictors, whereas there are initially, for instance, I have 20 variables in the beginning, and then I will select only Q of them. Q is necessarily smaller than P, otherwise there is no, this is not a random forest algorithm. And then you train a model on each bootstrap sample, and at the end you aggregate the decision tree or the hypothesis by averaging if you have a regression or by the majority voting rule. How to choose Q with respect to P? Everybody understand? Q is a number of features that I will use to train the trees on the bootstrap sample, and P is a number of features, a number of variables that I have initially. In general, we have some decision rule like this. We choose Q is equal to square root of P, or log 2 of P, or P divided by 3. Okay? This is why, remember, here we have a random forest with max feature square root, random forest with a max feature log2, and random feature with a max feature none, which is, this is not a random forest, this is a bagging model. This is a bagging here. And the other, so the bagging is here. You understand why this is a bagging? Because when I do not impose a constraint on the maximum feature considered for each trees, so it means that P is equal to Q. Okay, so at the beginning, I have X1, X2, XQ. This is in my training data set, okay? When I make my bootstrap sample, I have also Q variable. So I necessarily consider the age, the funding amount, etc. So here, in green line, you have the out of bag error of bagging, standard bagging method. Now, if I say, okay, for instance, I consider the blue line, so max feature is equal to square root of P. So for instance, so Q is equal to the square root of P. So this is, in this case, a random forest. Why? Because, for instance, if Q is equal to 4, I have to select only 2 variables. So I will select, for instance, X2 and X7. Okay? But I don't have all the variables initially available in my dataset. And you observe, for instance, the blue line, okay, here, but the out-of-bag error is always smaller than the out-of-bag error of the bagging. Why? Because you have reduced the correlation of the decision tree. Okay, let me go back to the slide. It's clear for this idea to reduce correlation and to consider this rule. This is an option of scikit-learn algorithm. Is there any question? Okay, so I propose to take a break of 10 minutes and then go back and to finish random forest and to apply it with Python. See you in 10 minutes. I had a problem with my Zoom, so I think that is okay now. Thank you for letting me go back to this webinar. Thank you very much. So let me resume. So is there any question about the idea and the advantage and the reason why you use a random forest and the advantage of a random forest with respect to a bagging? This time, this is a reduction in the variance, in the correlation between the trees on the bootstrap samples due to the fact that you do not consider all the features available in the training data set, and you make a constraint on the trees, on the choice that it could make, and the CART algorithm could make among the feature. And by putting this constraint, then you have necessarily different decision trees with different decision. So a low correlation, and a low correlation means that the variance of the bagging, so the variance of the random forest, will decrease much more than if in the case that simple bagging in which you don't impose this constraint. Okay, so if you want to implement a random forest with scikit-learn, you have a random forest classifier. You have also a random forest regression, okay, or regression problem. So I think that now you should understand all the options of the scikit-learn functions. So n estimators, this corresponds to my b okay, parameters. By default, it's equal to 100. Criterion Gini, by default, this is the impurity criterion that you could choose. So by default, it is a Gini, because in the CART algorithm, we use a Gini index of impurity measure, but if you want to change it, you can change with this option. Max depth, this is the option that puts a constraint on the maximum depth of your decision tree trained on all the bags, the bootstrap samples, okay? By default, this is interesting because by default, the algorithm random forest classifier put no constraint. And so there is no pruning, no pre-pruning or post-pruning. And so we have a very, it tends to be in favor of tree with a large depth. And so a low bias due to the fact that we'll reduce the variance with a bagging argument. But we have also the minimum sample speed, the minimum sample lift, etc., which are minimum weight fraction lift, which are the standard options that we have already seen for the decision trees. This option are not specific to the random classifier, to the random forest, but to the trees. And since the random forest is an aggregation of trees, you have the same options. The more specific option is the next one, which is max feature. So max feature, you have three choices: square root, log2, none. By default, it is fixed to square root. So the number of variables considered in each bootstrap samples correspond to the square root of the total number of initial variables available in the initial data set. If you put none, okay, that max feature, so Q is equal to P, and then you have a bagging algorithm. Be careful because, okay, if you put here this option, you no longer have a random forest, but you have a bagging, okay? And you will find approximately the same result as with the bagging classifier functions that I presented yesterday. Okay, and so then you have other option, max lift nodes. This is also an option which was present in the CART algorithm. Mean impurity decrease. This is a constraint to consider if there is a split only if there is a minimum impurity decrease. Bootstrap, true or false. So bootstrap, if you put true, this is a bootstrap sampling, and you have a random forest. If you put false, this is not a random forest because, okay, you don't have a replacement. We have an option that is OOB. OOB score false. This is an option that is related to the out of bag error. Is just want to make an assessment of your error on the out of bag. And then for the rest, I let you CCP. This is cost complexity parameters that control for the post pruning that you could implement for each tray trained on the bootstrap sample. Do you have any question about these options? So the only new option is this one, max feature. Do you have any question before we start? No? So how to implement. This is always the same structure with scikit-learn, two-stage. I declare a structural form for a given model. This is a random classifier here. And then I ask first to fit, then to predict, or many other things, okay? But this is the same syntax. My structure point, fit, point, predict, point, etc. So here from scikit-learn, I import the random forest classification. This function make classification is just a small function that allows you to generate some data, okay? When you don't have a test data set, you use this make classification that generates a data set with X and Y with 4 feature, etc., blah, blah, many options with 1,000 observation, 4 features for a classification, d'accord? But this is not my first order here. Here, I consider a random forest classifier function with a maximum depth equal to 2. I control for the seed in order to reproduce my result. This is particularly important due to the random sampling. And then I let the other option by default, etc. This declare a structure of a random forest. This structure of a random forest is stored in the variable CLF. And then I ask to Python to train this model with particular data, X and Y. So the syntax is always the same. My model structure, so CLF here, point, fit into brackets, X and Y to fit my data set. Okay. Then I can also ask to predict. Okay. So this is always the same syntax. The name of my structure. So here is CLF, but whatever the name, Toto, point, predict, Toto, point, fit, etc. And here I give the value for the 4 features. So X1, X2, X3, X4. So it corresponds to an individual. And then this program will report, print the value of the forecast Y for this individual, where X1 is equal to minus 1.9, minus 0.5 for X2, 1 for X3, and 10 for X4, etc. Is there any question? Maybe I finish with some comments. So, pruning under scikit-learn, okay, the default values of parameter controlling the tree size lead to fully expanded unpruned trees. Okay, why? Because max depth is equal to none, and minimum sample length is equal to 0, etc. So, 1. So, okay, there is no constraint on the size of the tree. Okay, so in general, if you put an option, you will obtain very large trees or depth trees. And so sometimes it's better to control for that and to reduce the complexity of the tree size, and to also to reduce the variance, because okay, you have the reduction of the variance with the bagging algorithm ID. But if at the beginning the variance is important, even if I multiply this variance by a correlation that is low, then at the end I will have also a big variance and a big problem of overfitting. Okay, so I recommend you to reduce a little bit the size of the trees by controlling this option of max depth, etc. So the reproducibility, so the features are always randomly permuted at each division, etc. So to achieve a deterministic behavior during fitting, you must state a random state and to obtain the same result if you rerun your code 2 years later or 2 months later. What are the advantages of bagging and random forests? So first, ease of implementation. So with one line of code with Python, you can run a very efficient algorithm that combine predictions from a large number of models. So as I said in the introduction, it is well known even in econometrics that when I combine several forecasts issued from very different models, my forecasts are in general very robust, and that's why the random forest works well. You have second argument, it is a variance reduction, and this is due to variance reduction because the bagging of the random forest reduces the variance of a given learning algorithm. And this is particularly useful when you have high dimensional data, so many variables or many individuals, because in this case, the standard algorithm tends to overfit. And so there is a lack of generalization to new data set. What are the limits of the bagging and random forest? The first limit or disadvantage is the loss of interpretability. When I run a random forest, at the end, I don't understand how the model works. What is the link between the car price and the default? And so it is necessary to use an interpretable machine learning method, so at the minimum feature importance, but okay, other type of method. This is computationally intensive. When you increase the number of bootstrap samples, you have to re-estimate each time your model, etc. So it could take time. It depends on your size of your data, type of the model that you bag, but to random forest, even for a decision tree, okay, it could be time consuming. So in general, we do not use bagging for real-time application. So for instance, if you want to implement a real-time fraud detection algorithm, you will not use a bagging model. And it is particularly important if you implement a random forest on your own computer to think about the parallelizations of your calculation. There are some options with scikit-learn. Okay, if I remember well, you have some option to control for the parallelization of your code. Okay. Less flexible. So bagging works particularly well when algorithms that are not very stable and have low biases, and algorithms that are more stable are subject to high biases, lead to poorer results. Okay. This is the idea that okay, we don't have to bag a linear model or logistic regression. So if you have any question, otherwise I will summarize the main concept. Random forest is a form of bagging in which you have a sampling on examples, but also a sampling on predictors. You have also the marginatory vote. You can also determine an out-of-bag error. You can also implement the feature importance measure, and there is a loss of interpretability. But random forest is often considered as the one most performing machine learning algorithm for a tabular dataset that we generally use in economics and finance. Is there any question? No question? So, if there is no question, let me go directly to the application. So, on the left of your collab, you have here all the text boxes that are used in the notebook Jupyter, and you have also some titles and subtitles. Okay, and so on the left here, when you click here on the outline, So on the left here with this button, you have the outline. And here I have a part that is exercise 3 random forest. And then I run here a small text that maybe you don't have this part of code on your own notebook, because I added this code this morning. But let me discuss. So remember that we have a X train, Y train, which is the training sample that corresponds to a training sample. And so I can, as I discussed a few minutes ago, so store in a variable rf a random forest classifier, and I declare some options. So here I declare, for instance, that, okay, I want to limit the size of the tree to a maximum depth to 5. I control for the seed, for the random state. I fix the value of 42 that I've previously defined. And then I ask directly, this is, I put the 2 stages in one line because I ask to Python to fit this model directly with X train and Y train, and then to store the train model in RF. So in RF, I don't have the structure of the model, but the train model. So this is okay. It is impossible for me to represent this model. This is why this model is not interpretable. I can produce a graph with a decision tree. Why? Because there is 100 decision tree. Remember that, okay, the n estimators option is equal to, by default, the n estimators is equal to 100. So I have 100 decision tree, and my model is an aggregation of 100 decision trees. So I cannot produce for you a graph. Okay, this is the idea of interpretability of the black box model. There is no link. Is there any question? The only thing that I can do is, okay, to consider some X data set, so a test data set, to introduce the X, so the feature, in the model RF, and to ask to Python to put some predictions. This is the only output that I can show you. And then I store in predict test the prediction, so it's a binary variable, 0, 1, produced by this random forest model. I store in a data frame this prediction. So the prediction here I stored with a colon with y underscore pred, and then I relate with index of the X train. This is just to create a data frame, and then I concatenate this data frame with y test just to see if y test is a true value of 0 of the default or not. So the test data set and the X data set in a variable, in data frame that is data underscore pred underscore test. And then here, I just display the 10 first line of this data set. So here, I have the prediction done by the random forest, the target variables, and all the X variables for the individuals of the test set. So for the first individual, the prediction of the model is 0, the true value is 0, the second model is 0, whereas the true value is 1, so there is an error, etc. Is there any question? It is not really visual. It's difficult to see something with a random forest. There is nothing to see. Okay, just we have a model, it is trained. I put a X and then I get a prediction. Okay, that's it. All this theory for that. No question? Okay. So Let me compute the accuracy on the test set. Let me compute, so I compare the Y on the test set to the prediction issued from the random forest. To compute the accuracy, remember that the accuracy is the percentage of correct classification. And the IUC is kind of R squared now for a classification model. 0.5 is the model, is a random generator, and 1 if the model is perfect. And here, on the test set, I have an accuracy of 80%. So I have 80% of correct prediction, 1, 1, and 0, 0. And the IC is equal to 0.58. I have no idea if it's good or not. This is not the question. It's just to show you how to implement a random forest. Okay? No other question? Okay. So here, this is a function that I defined before, a modelization. Remember, this is a kind of aggregate function that first declare a model, then train it on the trained data set, third, make the prediction on the test data set, and finally, compute the accuracy and the IUC on the train and on the test. Okay? So, what are the options? I use this function modelization for a model that is my random forest. Okay? X-train, X-test, Y-train, Y-test, and I control for the seed. Okay, here I put no option. Okay, so there is no option in the random forest classification. It is, I think that I can, if I withdraw here the maximum date option, so I rerun the code, and I rerun the accuracy. Okay, and I think that we will find, I don't understand why we don't find exactly the same. It's strange. There is a strange thing here. I don't know why we don't have exactly the same results. Maybe the seed, but seed it's okay. There is a mystery. I don't understand why we don't have exactly the same value here, but okay. There is a mystery. I will not find in a few minutes the solution. Okay, so let me go back here. So, okay, I rerun a random forest. I guess that is there is no option, so no constraint. Okay, and so as you could observe, the accuracy on the train is 96%. The accuracy on the test is 80%, and the IUC on the train is 0.999. So near a perfect model, but on the test, there is a decrease. So if I put the option, I have an overfitting issue as for any machine learning algorithm. Okay, this is not magic, as there is no magical with random forest. If I run the random forest, why no controlling for the hyperparameters, then I will have, in general, an overfitting, even the random forest reduce the variance of the model. So we will analyze the performance of the random forest when we increase or decrease the depth of the trees. So for that, I have considered a loop on the depth from 1 to 31. Okay. And then I consider a random forest, but here, each time I change, it is okay. I run with okay 1 max depth, then I run with 2, etc. My step, etc. This is a loop that do exactly that you can do by yourself manually. And then I consider for each, I make the forecast on the test, and then I store the accuracy on the test, on the train, and the IUC on the train of the test. And I store in these elements in these variables, whatever. And now I produce some graphs, okay? Sorry. It takes a few minutes, and I didn't run all the codes before the webinar. Sorry. So we have to wait for a few minutes just to see this part. Okay, and so now the loop is over, and so I reproduce here the accuracy depending on the depth of the trees. So from 1 to 31 for the train and for the test. What is your recommendation about the maximum depth that you could use here? You should. Yes, Fatme?
I think we should use 5 because after 5 they start to diverge.
Yes, exactly. Okay, so here, this is an evidence, and this is like a cross-validation, okay, but okay, you have to make a loop, etc. And then this is an evidence that, okay, to control for overfitting, we have to fix the value of the random forest to 5. So let me here fix to 5. So we will use this option, depth here. And so, okay, remember if I put no constraint, I have this divergence. If I now rerun this part of the code with depth is equal to 5, then I reduce and I obtain approximately the same value for the accuracy and for the IUC for the train and the test. And this is a very nice model because we have a good fit, but this fit is also valuable for new data, okay? You understand the general idea to way to proceed for the machine learning algorithm? This is a way to do is just to compute, to make a loop, to evaluate your model out of sample, so in try test sample, and to for different value of the hyperparameters. Here's the decision, the depth of the tree, and then okay to determine graphically an optimal value. Then you can use the second option, you can use a cross-validation. And third, you can use the out-of-bag error. Okay, so you have 3 approaches to determine the hyperparameters. If I use the same graph for the IUC on the train in blue and the test in orange, then you have approximately the same diagnostic. Okay, and I recommend you to use a 5 or 6 for the decision, for the depth of the decision tree. Is there any question? No. Yes, I don't remember what it is. It is, okay, we run the IUC on the test. This is just to make, okay, a focus on the orange line, okay? So this is here, the same graph as in here, but I do not report the IUC on the test just to avoid the fact that the scale is too small. Okay, so and then you observe that okay, indeed, we have to fix to 5 or 6 the the optimal value of the decision tree, of the depth of the tree. Now, okay, so I remember that, okay, for to fix the value of the hyperparameters, so first I do a loop and I assess the value of an error or IUC, MSC, R squared, whatever on the test set, and I, okay, graphically determine the optimal value. Second, I use a cross-validation. It is easier to use a cross-validation because there is a built-in function in scikit-learn, okay? And then you can use hold out, the leave one out, or the scaffold approach. So here I use a scaffold with 5-fold cross-validation. So first, I declare my structure of random forest classifier with no option. I put I store the structure of my model in the variable rf. I declare a grid on the value of my hyperparameters. I have considered here one hyperparameters, but I can also consider other parameters. You can have a 2-dimensional grid or 3-dimensional grid, okay? But here, for to simplify, I only consider the max depth, and I use a grid that where the maximum depth range from 1 to 16. Then I use the grid search CV. Okay. Grid search CV, it's a built-in function of scikit-learn that it is a kind of loop, okay, in which you will assess the error, the cross-validation error with a scaffold approach, okay? And so to determine the optimal value of the hyperparameters. So I use a grid first. What is the model? It is RF, so my random forest here. What is the grid of parameters? It is parameters here. How do you want to use a scaffold? Yes, I want to use a scaffold approach. What is the number of folds? 5, okay. End job, it is an option for the parallelization of your score, then scoring is just okay. And then you fit the best model, okay, using the optimal value of the hyperparameters determined by grid search value, you fit on the trained data set. And then RF fit, it corresponds to the best model obtained with the optimal value of the hyperparameters. If you want to get the hyperparameters of the optimal model, you just have to put best estimator, okay, and just give you here what are the optimal value. And as you can see, the cross-validation choose a maximum depth of 11. Let me illustrate here. You can see that according to the IUC on the test set, okay, the cross-validation tends to choose a value here. Be careful, as this is not exactly the same. I think that you have understood, but okay, maybe I will explain. Okay. Okay, when I do my graph, okay, I train my model here, okay, and I evaluate the error here, okay. Okay, when I do a cross-validation, remember that, okay, I have false, etc., etc., and then I use different parts of the data as a training data set, as a validation data set, etc. So there is no reason that the optimal value with this exercise of the hyperparameters corresponds to the optimal value determined by the cross-validation. Okay. How do you choose between 5 or 11? For instance, one method say, okay, you have to choose 5 for the maximum decision depth, and the other method, the cross-validation, say, oh, no, it's a model with max depth equal to 11. How did you choose? Do you choose this? How to make a choice between the two approaches? It's difficult. You have an idea? Well, I recommend in this case to run the two models. For instance, here, I run a model with with maximum depth of 5. Here, I have a model with 11. I observe that there is a better, I have better IUC on the test set, but part of overfitting, little overfitting. So maybe, for instance, I will recommend you to use 5 in this case. But okay, there is no. Sometimes the machine learning. This is the difference with econometrics. Sometimes machine learning has the same approach as a cooking. So okay, I put more salt, more sugar in my cake, etc. So there is no theoretical foundation for some arbitrary choice. And at the end, you have 3 different methods to determine the value of the hyperparameters. You have 2 different results or 3 different results. At the end, you have to be lucky and to find the best parameters. No question? Okay, so the last model is this one with I don't remember what is the last model, but whatever. And given this model, I make some prediction. So I take the model RF fits. So I'm sorry, RF fits. The last RF fits. I guess that it is where is RF fit? I remember RF fit. Where is RF fit? Is here. So it is the optimal model issued from the cross validation. So optimal model with 11 lags. If you don't want this choice, you just have to re-estimate a model, random forest with 5 max depth, and just consider this is your fit. And so here I ask with this model to make some prediction on the train, prediction of the probability on the train, so predict and predict proba, and then to only reproduce here. We do the same. We predict on the test, we predict the probability on the test, and we concatenate all this data in a data framework, data pretest. And here you have the prediction with the best model, the true value, the probability, and the value of the X. Is there any question? No question? I evaluate the performance of my random forests on the test and on the train. So this is the same that I presented before. Okay. So I have another fitting. That's why maybe I recommend you to decrease, but okay, according to the cross validation with a careful approach, this is the best model. Okay, so I don't. Okay. Then we use a high modelization to do exactly the same, but there is no particular advantage to use this this code here. And okay, now I show you how to produce the feature importance. Okay, so you consider here your best model, and there is a possibility to use this function, which is feature importance on your model. So this is always the same syntax. You have the model which has been estimated, and then you put feature importance. I stored the feature importance because the feature importance is a value, okay? And then you have many possibility to graph this feature importance. We'll find And what is the most important? What are the most important variable in my credit scoring model? First, the funding amount. This is the MDI, so the mean decrease in impunity, with a mean decrease in impunity of about 18%. The second variable is age, monthly payment, card price, job tenure. And I guess that, okay, with long duration, maybe, that these 6 variables explain 80% of the decrease in impurity of my model. Okay. These variables are most important in my random forest. So if you want feature importance, if you want, there is many way to okay, you have this type of graph that you could implement, okay, with Panda, with okay. You can do some other feature importance based on permutation of the model. This is another concept. That's why it is important when you say, okay, I have some feature importance, to explain which type of feature importance. If it is an MDI, okay, but there is also feature importance based on permutation of the model, whatever. So there are many ways to compute the feature importance. Okay, in general, they give approximately the same diagnostic about the model, but you can do very different graphs of the feature importance, and I let you to explore this possibility with scikit-learn. Do you have any questions about the implementation of a random forest with scikit-learn? No? Okay. No question. So maybe I propose to take a break, 10 minutes, and then we will go back to the theory to present an alternative to the random forest that are the XGBoost model and the boosting approach. See you in 10 minutes. Okay, I propose to resume. So this is the last part, last section of my webinar, which is devoted to the boosting. I'm sincerely sorry to present this method at the end of the last session of the webinar, because, okay, and I hope that you are not too tired, because this is the most complex approach compared to the other, okay? I will try to give you the general idea, and maybe I will not present all the details of the XGBoost, but only of simplest algorithms, that is AdaBoost. Okay, so I propose to, in 1 hour, just maybe to understand the concept of boosting. Maybe I will have to the time to detail a simple algorithm that is the AdaBoost. And when the basic idea is to weight the examples, and you have a classifier rating, okay? And then we will understand. And once we have understood the AdaBoost algorithm, then I will, in few minutes, present the XGBoost. And on the Google Colab, I think that we will not have the time to present you the application of the Google Colab, but on the Google Colab here, you have some codes to implement an XGBoost model, okay? Okay. So this is really easy, but okay, to implement, this is always the same idea. You have to declare the model, and then to fit it, or to make a grid search on some parameters, etc., etc. So let me start with the AdaBoost. So what is boosting? Boosting is an iterative method. This is the main difference with the bagging. The bagging, there is no iterations. You have a bootstrap sample and you compute an average decision. Here, you have an iterative method and you aggregate several models. And here, the difference with the bagging is the aggregation procedure is adaptative rather than parallel. And the general idea is to combine several weak hypotheses or weak models with a weighting proportional to the predictive power. Okay, so you will combine some model with a weight, and the weight depends on the predictive power of this model. So in bagging, you have bootstrap sample, and with a bootstrap sample, you train some classifier, and at the end, you have many classifiers and you make the average. The boosting, that's why we say this is a parallel approach, okay? Because I can run in parallel many classification tasks. With the boosting, this is an iterative approach. I consider all the samples. Then I run a first classifier. With this classifier, I made some errors. And then I consider the same sample as before, but I introduce some weights and I put a big weight to the example, to the individual for which the previous classifier made some error. So for instance, I made a big error for this individual, a big error, okay, for this individual, a big error for this individual, a big error for this individual. So this individual will have a high weight. On the contrary, I do not an error for this when I forecast the price of an house. Okay, I made a small error for this house, a small error for this house, a small error for this house, and so this observation will have a small weight in the second stage. Then, with this weight, with this weighted sample, I run a second classifier, and the idea is to try to force the model to give more weight to the observation for which the first classifier was poor, okay, was not effective or not efficient. And then this second classifier made some error, sometimes on the same point, sometimes on different points. So we have an error here, an important error here. Okay, so I define another sample, weighted sample, in which I put a high weight to the observation for which the classifier at the second stage made some error, and few and small bias, small weight to the observation for which the classifier make small error. And then I run a third classifier, and so on and so on. Okay? Did you understood global idea of the boosting? No question? Okay, so the boosting was introduced by some works of Freund and Shapir in 1995. And the first boosting algorithm was AdaBoost. And it was developed by Freund and Shapir in 1996 and 1997. But a very often used boosting algorithm is a gradient boosting, okay, method applied to decision tree, and this is called what we call the XGBoost, extreme gradient boosting. And the extreme gradient boosting was developed by a firm that is DMLC, based, and this firm has produced a Python code, okay, to estimate this XGBoost. And this XGBoost was based on the work of Chen and Guestrin in 2016. Okay. Any question? So let me start with the AdaBoost. So it is a meta estimator. Okay, it is an ensemble method that fits a weak classifier. In general, it is a very simple model. Typically, it is a one-node tree, what we call a decision stump. What is a decision stump? Is a tree with only a depth equal to 1. This is a decision stump. We train this model to the original data set, all the data. There is no bootstrap sample. And then we train additional copies of this classifier on the same data set, but overweighting the misclassified instances so that subsequent classifier focus more on this predictor error. So I have a decision stump, then he made some error, then I will train another decision stump with a focus, etc., on the misclassification error done by the first model. This is a decision stump, the decision tree of depth 1. So we consider the initial data set. We run a decision stump. A decision stump say, okay, let us imagine that there is two variables, x1, x2. Right. Then you have a decision like this, for instance. Okay, and here I made an error because, okay, I predict it is 0, for instance, and the true value is 1. So then I consider a weighted data set in which for this individual, I put a weight larger than for the other individuals. And then I train a second model. Okay. And at the end, I consider an average of these two models. And for instance, the decision rule of the strong learner issued from the boosting of the AdaBoost algorithm is the following. And then you see that there is less error than it was done for the first with any weak learner in the first stage or second stage. And with the iteration process, you will reach a model which is more efficient than the previous model. Any question? So now weight and upsampling. So the examples, so the individual in training data set are weighted by a weight omega I. The sum of the weight is equal to 1. So when I ask, when you think about a weight, what does it mean? It is as if we had a column to the data set containing the weight of each row. What does it mean? For instance, let me go back to, let me just a few minutes try to, okay. Let me go back to my data set. What does it mean to have a weight? Okay. Let us imagine that you have another column here that is a weight. Okay. And here, let us imagine that I have 10 individuals. Okay. And at the first iteration, they have all the same weight. In the second iteration, let us imagine that I made an error with the first classifier for the individual 3. So I will increase its weight. For instance, I will put 0.3, and thus I will say here that I have 1 minus 0.3 divided by 9. Up. Okay, and I have this type of formula, quoi. And at the end, the sum is equal to 1. What does it mean? What is the idea? The idea is the fact that at the second stage, Christophe Hurlin here, individual number 3, has a weight larger than the other, but what does it mean in practice? In practice, it is like if you have, what is the ratio between this weight and this weight? For instance, if I divide 0.3 divided by 0.8, it is 3.75. It is like if you have another sample in which you have 4 times Christophe Hurlin. Okay? Okay. 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 With the same weight as the other. Okay. This is the idea. The idea, when I put a weight of, which is 3 times the weight of the other individual, it is as if I duplicate the individual number 3 in my sample 3 or 4 times. Okay. And so when the classifier will try to find the optimal decision rule, it will give more weight to this individual because this individual is replicated 3 or 4 times, depending on the ratio of the weight. Do you have any question about this idea of weight? No? Great. Yes, Ahmed.
Would boosting be reasonable to use if I want to fix something like unbalanced datasets? Doesn't it?
Whoa. Whatever the algorithm, bagging or boosting, the fact to use this algorithm on unbalanced dataset, what is an unbalanced dataset? In case of classification, it is a dataset in which the proportion of 1 is very, very, very small compared to the proportion of 0 in the initial dataset. Okay. For instance, I have a default rate in my dataset of 0.05. Okay. In this case, there are 3 consequences. The first is that some assessment criteria are no longer valid. For instance, the percentage of correct classification is not a good measure for the performance of the model. Why? Because a model that say 0 for, that predict 0 for all the individuals, because this is a useless model, will have a percentage of correct classification of 1 minus the default rate. So if, for instance, the default rate is 1%, the percentage of correct classification of a very stupid model that predicts 0 for everyone will be 0.99. So the percentage of correct classification, for instance, is no longer valid when you have an unbalanced dataset. So some criteria are no longer valid. The second consequence is that it has an impact of the unbalanced dataset has an impact of on the training of the models. And for some models, the fact that you train the model with on unbalanced tends to lead to low performance. Okay. It is true that the unbalanced data, the XGBoost is sensible to the use unbalanced dataset. Why? Because it's complicated because it depends on the structure of your data. Yes.
Sorry, is it sensitive in the sense that of being bad or sensitive in the sense of being good? I expect something like boosting would be suitable because the class with fewer instances are likely to be misclassified. So I expect ARA boosting to give them more weight at later stages so that it kind of fixes them.
You're right, but in general, it is not. It is a reverse effect that you have. it is the fact that when a classification in which the zero are in majority, the model will tend to put zero to everyone. And then the majority class will be well classified. On the contrary, the problem is more with the minority
class.
Yes, exactly. And so in this case, it is true that, okay, the fact to weight, the baseline idea of the boosting is to weight, to overrate the misclassification error. In this general, it is related to the minority class. But if the class is really is really rare, then the overweighting is not sufficient to distort the attention of the model to this class. I don't know if I have okay. If it's clear.
Okay, so what you mean is that
because
the majority will
yes.
all if we say try to fix the model so that it classifies minority, then we will find out that we have misclassified more of the majorities, so the model will return the weighting to the majority class once again.
Exactly.
Okay. Okay. Thank you very much.
So initially, all the individuals have the same weight, and at each step, we recompute the weight. So this is an upscaling phase, depending on the error made on the previous step. And this is a formula for the upscaling. So the weight at stage T, the weight of Christophe Hurlin, so individual I at the stage T+1 correspond to the weight of Christophe Hurlin at stage T, divided by the normalization factor, whatever, times expectation of minus alpha T parameters, whatever, which is product of yi, so the true value for Christophe Hurlin, times the prediction of the model obtained at the stage T. Okay, so what does it mean? If y and y hat are equal, so equal to 1 or equal to 0, then this formula is the following. So we have exponential of minus alpha t, okay? And otherwise, it is exponential of alpha t. So remember, the exponential is always positive, but if I have exponential of minus infinity, it tends to 0, and so on the contrary, exponential of a positive number is larger than exponential of minus this number. Okay, and so the weight here is higher than the weight at time t+1 in the case where I'm well classified at state t. It's clear or pas, or not? You have any? A case of well classification is a case, for instance, where y and y hat is equal to 1. Okay, so this part is equal to 1. Okay, so I obtain this formula when otherwise I have 0, 0. But okay, it is not this is my my focus is here, and yes, I missed something here. There is a problem with my notation. Okay. I think it's okay. Do you have any? Do you have any question about this upscaling mechanism? I have an example in a few minutes. Okay. The normalized factor is just a factor such as the sum of the weight at each step is equal to 1. Okay. So the weighting coefficient alpha t depends on the classification error in step t. Okay. And the formula is the following. So there is a link between what we call the weighting coefficient and the classification error. Okay, I will skip this part. Okay, so okay. Let me describe the ADABUS algorithm. So we start with a train sample. We normalize the weight for all the individual to 1 divided by L. We train a decision stump with the initial sample in which all the individuals are the same weight. And we have H1, the first decision stump, okay, the model. So at this stage, the model, the algorithm, we just, for instance, take age, okay, and a threshold, okay, and then deduce two subpopulation, okay? And for instance, on the left, there is he predict a default, and on the right, the model predicts no default, okay? So this is the first model trained with, so this is the H1 model trained with a sample in which all the individuals are the same weight. Then you compute the error, epsilon 1, okay? So we compute the error, and you have the individual for which there is a misclassification. We compute the sum of their weight. Do you understand? So let us imagine that I have 3 individuals for which this decision stump made an error based on the age. Then I sum the weight of these 3 individuals. So at the beginning, they have, for instance, if there are 3 individuals for which there is an error, for which y is different from the prediction of the model, their weight is 1 divided by n at the beginning. So what is epsilon 1? Epsilon 1 is the sum of their weight. So it's epsilon 1 divided by n plus 1 divided by n, 1 divided by n. So this is equal to 3 divided by n. It's clear? This is the sum of the weight for the individual for which there is an error. Then we can define what we call the weighting coefficient. The formula for the weighting coefficient is the following. Alpha 1 is 1 divided by 2, the logarithm 1 minus epsilon 1 divided by epsilon 1. This gives you a value. And this value is applied to this formula to determine the weight for all the individuals, all the participants have a new weight. And the weight at stage 2 is the weight at stage 1 times this formula divided by Z1. You consider this new data set and you train a new decision tree, so a new decision stump, a new model with only one depth. And H2 is a model trained at the second stage, etc. at the end, this is really simple. The ADA boost meta classifier is given by the sum of all the decisions done by all the models times this coefficient alpha t. Okay. So the most kind of error provided by the model. Okay. And so this is a weighted sum of the boosted model. Okay, so at the first stage, I have H1. Okay, H1, this is simply a decision stump based on the age. Okay. At the second stage, okay, I train a model, and the model is also a decision stump based this time on the car price and the threshold of 10,000 euros. Okay. And so I have an error rate, alpha 1, alpha 2, and my model at the end is simply the sum of the decision given by this model, H1, times the error rate alpha 1, plus the decision given by this simple model times the error rate given by this model, etc. Is there any question? So there is a double weighting scheme in the bootstrap, in the boosting. You weight the individuals and you weight also the models. Okay, there is a weight for the models and there is a weight for the individuals. Is there any question? I think that I have an example. Okay, so we have a classifier weight. Do not confuse alpha 1, alpha m. This is a classification. What we call the alpha parameters are called the weighting coefficient. Okay. And you have also the example weights, omega 1, omega 10. Okay. This is the formula for the normalization factor. This is 2 square root of 1 minus epsilon t times epsilon t. So let me illustrate the boosting with ADA boost with a simple example. The weight is to predict a disease. So this is a classification problem as a function of gender, age, income. We have, let us imagine a very simple example in which we have only 5 individuals. At the beginning, the weight of all the individuals is equal to 1 divided by 5. This is 1, this target variable is equal to 1 for individual 1, 4, and 5, 0 for the others, and you have the gender, the age, and the income. We create a decision tree of depth equal to 1 for each of the variables and compare these trees and the basis of impurity measures. And we choose the best models, and the best model is the first decision tree on my boosting strategy. Let us assume that the first classifier, I don't know what is, but let us imagine that it is based on age, okay? So this is a decision stump based on age, and you have a classification, and you have a single classification error over the 5 instances. Okay, there is only one individual for which there is a classification error. So what is the total error? Epsilon 1 is the sum of the weight of the individual for which there is an error. There is only one. There is an error for Christophe Hurlin. The weight of Christophe Hurlin is 1 divided by 5. So the total error is 1 over 5. Then I can produce the alpha 1, which is the weighting factor. Okay, it is 1 divided by 2 logarithm of 1 minus epsilon 1 divided by epsilon 1. This is equal to 0.69. The normalization factor is 2 times 1 minus epsilon 1 times epsilon 1. This is equal to 0.8. Now I compute the weight for the next iteration of my individuals. For the 4 well-ranked instances, the weight is the following. So the new weight at stage 1 is a formal weight. So 1 divided by 5 is 5, divided by Z1 times exponential minus alpha 1. So minus 0.69. So the new weight is 0.1254. So for the 4 people for which the first model was good, makes a good prediction, the weight decreases from 1/5 to 0.12. So the weight decreases. On the contrary, the weight of the misclassified instance is, so the new weight is the initial weight divided by Z1 times exponential alpha 1. So it is equal to 0.49. So the weight increases from 0.2 to 0.5. It's clear? Next. Okay, so let us imagine that it is the individual for which there is a misclassification in the first stage. So now we have this weight for this individual and the other individual have a reduced weight. And now we redo the same. We determine, okay, a new model, okay, by considering gender, age, income. We compare this model based on the impurity decrease. We consider, for instance, that the best model now is based on income. We compute the error of classification. We compute the error of the alpha 2. We compute the weight, etc., etc. There is any question about AdaBoost algorithm? As I mentioned, the boosting is the most complex approach. This is okay, but the idea is to have very simple models to compute some error from this simple model, to weight the instance in examples, to retrain a new model, and at the end, the decision of the final model is simply alpha 1 times h1 plus alpha 2 times h2 plus alpha 3 times h3, etc., etc. So if you want to run an AdaBoost model, you can use AdaBoost classifier with scikit-learn. So you have a base estimator. If you specify nothing, the base estimator is, as you read here, a decision tree with max depth is equal to 1. So it's what we call a decision stump. The number of estimator by default is equal to 50. That is the maximum number of estimator, because okay, we have a loop, an iterative process, until which the iterative procedure stop when there is no change in the error. Okay, so if there are no improvement in the error, so the procedure stops. But in order to avoid infinite loop, you have to specify a maximum number of iteration. This is a maximum number of iteration. So the learning rate is something, okay, it's difficult for me to explain in a few minutes what is the learning rate in this case, because I didn't precise something here. But okay, there is no learning rate in my slide. Okay. So it's very easy. So you have to specify the structure of your AdaBoost model, to store the structure of this AdaBoost model with the option in a variable, and then point fit, point predict, point, etc. And that's it, because I cannot represent an AdaBoost model. This is also black box model, because, okay, there is no representation for an AdaBoost model. Do you have any question? This is really a very good model, because, okay, with this type, this combination of very simple model with decision stump, you can, for instance, have this type of decision boundary in which you capture well this cluster here of data. And this model, this decision is issued from the aggregation, iterative aggregation of a very simple model. And in general, the boosting is very efficient to, for instance, for a classification regression, but also for regression model. So, what is the idea of the boosting? The boosting is an iterative procedure in which at each step you change the weight of the examples, and to increase the weight of the instance for which you made an error as a previous step, and decrease the weight of the well-classified instance. At the end, the boosted algorithm model correspond to weighted sum average of the decision done by each weak model, weak learner. In general, the AdaBoost is based on decision stump. Decision stump is a tree with a depth equal to 1. You have weighting coefficient for the instance. You have a weighted error frequency, and you have a weight for the weak classifier. Okay, I don't have the time to present, I guess, in 10 minutes it will, the XGBoost, okay? But this is a particular algorithm of boosting. And it's complicated to explain in a few minutes the idea of how to, okay, to implement the gradient boosting. So it is not an XGBoost, it is a gradient boosting. You can use it with a scikit-learn, with a common gradient boosting classifier. And then there is a particular gradient boosting version that corresponds to the XGBoost. Okay. And for the XGBoost, okay, there is a penalization of the complexity, and the XGBoost is available on the website of DMLC. And the DMLC, and here, this is a command to run an XGBoost classifier. Okay. I think that I should stop here. Maybe read this part by yourself, this part devoted to the gradient boosting. Okay. If you have any questions, don't hesitate to send me an email, and I can organize with you even a call or whatever, or answer by mail, or answer with a call, because I think that it's not reasonable to teach you what is a gradient boosting in 5 minutes or 10 minutes, and at the end of on this session. This is a problem with the boosting, because it's more complex approach, and in general, it's not reasonable to teach boosting approach and XGBoost approach at the end of a training session. Okay, so I propose to stop here, except if you have some question. At least I hope that you have understood what is AdaBoost and what is the general idea of the boosting. And I guess that you will understand by yourself XGBoost and the gradient boosting in general. Is there any question? No? So I propose to stop here. So it was a pleasure to work with you.